Okay. A couple of slides to complete the part on the construction of flow duration curves starting from real observed data. Then we'll focus on the practical activity in R. Okay. If you recall, last week we saw briefly, quickly, how to construct, how to draw flow duration curves starting from observed data. We mentioned the fact that normally flow duration curves are built, constructed using daily stream flow series, and we saw how to draw a period of record flow duration curve, putting together all the observed data in a single sample, or how to draw annual flow duration curves from which then we can infer the typical behavior, for example, in terms of median curve, or some, let's say, more extreme behaviors, termed percentiles annual flow duration curves. In the diagram here, for example, doesn't move. Maybe now we are luckier. Let's try. Yes. In the example of this slide, the two percentile flow duration curves that are indicated with blue lines are the 5% percentile curve and the 95% percentile curve. You remember how we can derive them? We, duration-wise, we look at the discharge value that exceeds, in this case, 5% of the observation, so just a few, and is exceeded by 95% of the observation, okay? In case of 95 percentile curve, the other way around. So it's the curve that duration-wise, and it can put together pieces of different empirical annual flow duration curves, exceeds 95% of the observation and is exceeded instead in the 5% of the times. Okay? Sufficiently clear? This is an indication on the stream flow regime, and in particular the stream flow availability associated with a given duration for a particularly dry year. So can be interested if our water problem at hand deals with the pollution of a stream. The lower the amount of water, the higher the concentration of pollutants, okay? Or the navigability issues associated with a given river breach, or hydropower production, how bad it can go. Whereas this is a representation of flow duration curves for a particularly wet year, abundance of water. And please keep in mind that, as you see here, and I'll spend a few words more on this later, the vertical axis is log scale. So between two tick marks, there's a whole order of magnitude in terms of cubic meters per second, okay? From 1 to 10 to 100. Sufficiently clear? Okay. Instead of referring to the non-exceedance probability of a curve, 5% here, 95% here, since each curve has an annual meaning, we can also refer to return period in years. Have you ever heard of return period? What is the return period of a flood? This flood has a 100-year return period, okay? It means that the stream flow value, the stream flow value is on average exceeded every 100 years, but on average. Same situation here, okay? Instead of referring to the percentile associated with a 95% non-exceedance probability, we can refer to the percentile flow duration curve with a return period of 20 years. Okay? Return period is a concept that you have clear. You need more indication on that. It's just for variables that have annual realizations, so the annual maximum flood, for example, or an annual flow duration curve. So for random variable that have annual realization is just another way to express probability, in particular non-exceedance probability or exceedance probability. The definition of return period is here. It's the inverse of the exceedance probability. So the probability that variable uppercase x is larger than value lowercase x. Since it's the inverse of the exceedance probability for every year, it can also be seen as 1 over 1 minus the non-exceedance probability, right? So if the non-exceedance probability is 0.95, 95%, you replace here 0.95, 1 minus 0.95 is 5%, 1 over 5% is equal to 20. It means that on average I have to wait 20 years to see a flow duration curve that is above this one, okay? So it represents situation in very wet condition. Same reasoning you can apply for dry years, but the definition of the return period is the opposite. Meaning that if you're looking into dry condition and you are concerned about very low values of discharge, you are concerned about discharge values that are here below this curve, right? Because you are concerned that your stream flow can be highly polluted due to an inlet pollutant and the lack of water. So the definition in this case is 1 over the non-exceedance probability. Okay, do you see the difference? So the 5% percentile curve is again a 1 in 20 years flow duration curve, and is the flow duration curve that is on average not exceeded, nothing below on average every 20 years, okay? Of course, in order to extract these curves, you have to have at least 20 years of observation in your sample, because this is not an extrapolation of the behavior, it's just an interpolation of the behavior. You are extracting percentile from observation, so, okay? So you need several years of observation to do this, to perform this computation. Tell me if this is sufficiently clear. Okay. Last thing, I want to show you how we plot flow duration curves. There are more than 2, but these 2 are the most common ways to plot flow duration curves. You can use a natural scale on the vertical axis or a log scale in the vertical axis. So natural scale is seldom used because since there's a very large variability of stream flow values between high flows, floods, and average flows or low flows, the diagram is squeezed in such a way that sometimes you cannot tell a perennial stream from an intermittent stream, okay? Because this part is squeezed by the fact that the vertical axis is in natural scale, so high flows take all the space in the diagram. But in problems where the volume of water is important, it's a variable you want to look at, the natural scale or arithmetic scale has the advantage that the area below the curve is a graphical representation of the volume of water, okay? It is an integral of a discharge over a duration, which is time, essentially. So since this is discharge, this is time, and you're taking the integral of this function, so the area below the curve has a clear physical meaning. It's the volume of water, okay? In a typical year, if you use the median annual flow duration curve, or on the long term, if you use a period of record flow duration curve. Sufficiently clear? Okay. The other way is the by far most common way to represent flow duration curve on a semi-logarithmic plot. Why? Because then, in this case, you can see very well low flows and high flows. Okay, due to this alteration of the vertical axis, low flows and high flows have the same importance on the diagram. Sufficiently clear? Good. You have questions on this part? No. In case you tell me, okay? If you have doubts, questions, comments, please. So I am going back to our virtuale page. I opened up a practical activity on FDC, construction and prediction. Okay, let's have a look at the general, let's say, content of this page. I already told you that this is our study area. Do you remember? Where you see a red dot, it means that there a stream gauge is located for which we have observation of daily flows, long series, at least 5 years of observation, continuous observation of daily stream flows. Whereas the orange polygons are the watersheds that drain into that point. Okay? We have several catchment, which we name with the river name, Reno, it's River Reno et Prachia. Reno et Prachia, where is it? Code number 2. It's this little tiny catchment up here. We are near the Apennine Divide. Bologna is somewhere around here. This is the same river, Reno et Casalecchio, so further downstream, close to the city of Bologna. Then you have some, they're called this way, catchment descriptors. These are indices for characterizing a watershed. We will see how to compute them in GIS environment. A is the drainage area in square kilometers. Mean Z is the mean elevation of the catchment in meters above the sea level. Okay? So Reno et Prachia, I was saying before, it's a tiny catchment near to the Apennine Divide, meaning that the raindrops that fall here then flows in Tuscany, whereas raindrops that falls here and creates runoff flows in Emilia-Romagna. This is the Apennine Divide. Reno et Prachia is a very small catchment, not even 40 square kilometers, and it has a high elevation because it's a headwater catchment. Okay, more than 900 meters is the average elevation above the sea level. Then theta. Theta is an angle in degree. It gives you the aspect of the catchment, more or less. Okay, it's the orientation of the catchment relative to, I don't remember, is that relative to east?
I think relative to north.
To north? Okay. These are degree that indicates the, let's say, the direction of the average slope of a catchment. These catchments, they more or less point, most of them, in that direction. And theta is an angle that tells you, it's a morphological descriptor. It tells you the orientation of the catchment. MAP, I'm telling also the units of this quantities, but you have them at the bottom of the page. This stands for mean annual precipitation. So it's a climatic descriptor. It's a descriptor of the climate. It tells you on average what is the mean annual precipitation on the catchment in millimeters. Okay? This is a catchment at very high elevation, well, relatively speaking, high elevations. So due to orographic effects, you see it has a very high mean annual precipitation relative to the others. As high you go, the higher you go, the more normally on average it rains due to temperature drop with the increasing elevation that helps condensation. And this is instead another climatic descriptor is the mean average potential evapotranspiration. So still in millimeters, the amount of water that evaporates on average every year, if you recall from the first classes. Okay. Why are these catchment descriptors important? We will see later on. They can help us to make predictions for a catchment when we do not have discharge data. We'll see this later on. Right now, the first tasks are associated with the availability of data. You have data, let's see how to represent the stream flow regime. Okay? This is the description of the catchment indices I just provided you with. Here, you will have script for this practical activity that refers to one site in particular, Savio at San Carlo. Savio at San Carlo, it's catchment number 5, is this area here. Savio at San Carlo will be our target site for the practical activity. But all the material I provided you with, it's ready to be applied as it is written because it's flexible. The coding is not hard coding but flexible coding. It's already ready to be used for any other catchment in the data set. You just have to replace the number of the target site. Okay?
Also outside of Italy?
It may work outside of Italy too, provided that you have streamflow data. Of course, you can apply it to your own data set. If you have a daily streamflow series, I will underline a couple of important passages on this. You can definitely apply these scripts to any catchments where you have observed data. And for prediction in engaged catchments, you have to have a region of study like this one, where you have several catchments with observed data, each one of them with some daily streamflow series. Thanks, Abdi.
Okay.
Did I reply?
Thank you.
Okay, no, you're welcome. Okay, today we focus on task 1. Task 1, as I was saying, is representation of the regime provided that you have observation where you need them. In the river cross-section where you're performing your engineering studies, you do have data for multiple years. Using the available daily streamflow data, construct and represent on a semi-logarithmic plot, so the most common way to represent flow duration curves, as we were discussing before, the following empirical curves. Why empirical? Because those are based on data, observed data. They're not theoretical, they are empirical. So the first one is the period of record flow duration curve. The second one is the annual flow duration curve for a climatically speaking typical hydrologic year, so the median AFDC, and then point C, percentile AFDC associated with the non-exceedance probability of 10% and 0.9%. So these are the flow duration curves for the 1 in 10 most wet year or most dry year. similar to the theoretical slides. Instead of 5% and 95, here we selected 10% and 90%. Okay, so we're referring to a return period of 10 years. Flow duration curves that are exceeded above or below, depending on which one you're looking at, on average every 10 years. Sufficiently clear? You have questions on these parts? Okay, we will focus on task 1 and on target site Savio et San Vittore. Here, going back to my laptop, you should have downloaded to your system and stored since last week in a folder, in a working directory, these 3 files, right? We're there. You have this information. Okay, so the PDF is just a PDF file that tells you exactly the things we've seen from Virtuale. Then you have a script. Do you see the script? We will be working on the script soon. Point R, it means that's an R script. The script is very, very heavily commented, so every single passage should be clear. But since these are the first times we're working together in R, I will try to provide you with a description of what we are doing at each and every line. Sufficiently clear? Okay. And then we have the database. The database is an Excel file. I can open it. And this is what I see if I open the file. Let me increase the zoom. I just want you to see the structure of this spreadsheet. Please do not modify it, otherwise the R script won't be able to retrieve data from it anymore. So don't, whatever you do, don't press save. Okay? So it has a headline here. Code is a column indicating the conventional code for that string gauge. It reflects exactly this table. So 2 is Reno et Tracchia. As you can see, there's also the name of the string gauge. Year. Column year indicates the year of the observations. These are real world data. These are observed average daily stream flows. And column C indicates in which year these data were observed. Okay? Then, beyond column C, D, E, etc., you have, for a given calendar day, 1st of January, 2nd of January, 3rd of January, you have indicated the average daily stream flows, okay, in cubic meters per second. You see a comma here, but it's not really a problem. It will be digested correctly by R using that extension, that package you installed last week. Okay? You have questions on the structure? So basically, string gauge by string gauge, you have all the observation years and then the data. And then when for a station it's over, you switch to the next station. Savio et San Carlo will be our target site. And the data for Savio et San Carlo are from lines, row records 22 to 36. Okay, sufficiently clear? You tell me if you have doubts. Do you have doubts there? No. No.
The columns are only daily data?
Stream flow data.
Okay.
So you have, starting from column D on, you have 365 columns. Okay? You may ask, what about leap years? You know what a leap year is? What is a leap year? It happens every 4 years, and it's that year for which February 29th exists. We applied a common rule. February 29 is discarded for each and every leap year in the data set. This simplifies the computational part, because in that case, every year is 365 days long, period. Also leap years. Sufficient. Did you understand what I said? So do you have birthday on February 29th? Any of you?
A colleague in the other room.
In the other room, there's one guy. I'm sorry for the other guy. Here, for us, February 29th doesn't exist, okay? Because it simplifies a lot the computation. First thing I wanted to point out also for you on the data set. So daily stream flows, you discard February 29th on leap years, and also, in order to work, your stream flow series has to be complete. Okay, complete. Not a single missing value. So each and every day of the year has to be there. Of course, real-world data sets present gaps and missing values. Okay? How we operate? We applied some, let's say, subjective criteria. I don't remember them exactly, but let's say if there are 1 or 2 days in a row missing, we linearly interpolated the flow based on what we have. If we have more missing data than 2, for example, this is a subjective criteria. You can be more or less selective. If there's a whole week missing, you discard the year of observation. Okay? So we reconstructed the data. We infilled the data series when the missing data were just a few. If there were a lot of missing data, the year was discarded. This is why, if you look here, you don't have all the years. See, 2002, 3, 4, 5, 6, 7. This is complete. This one seems to be complete. Savio at San Carlo, our target site, 2002, 2005, because 4 and 3 probably were not complete. And if you want to know exactly the subjective criteria we applied, with some reasoning on it, because of course, if you linearly interpolate the data, those are invented data. So you cannot stretch that procedure too much. Do you understand what I mean? So if you want to know exactly what criteria we applied, ask Alan, because he was the one creating this data set. Okay? But the idea is this. If I lose a big part of the year, maybe, for example, during high flows, then I cannot consider that year for representing the average condition for anomalously wet years, for example, because there's a year in the sample with no data. So, in the data set, only complete years, no February 29, and that's it. Good. Good. So, I open up now. The other tab. The other tab is the descriptors, because we will be using those as well. So, in the second sheet, you see basically a table that looks exactly like the one we saw before. Good. Let's go back to RStudio then. I will run an instance of RStudio. Maybe by the end of the class. Okay. Let me maximize the window. Good. Are we here all with an RStudio instance running? Okay, we can clear with Control and L the panel of the console if we want to have more space. Then we want to open the R script, but more importantly, we want to set as working directory the directory where we have the data. Okay? R, without telling you, works in a home directory. If you don't specify and detail the path, it looks for files in its home directory. So let's do something like this. I write dir open and close parenthesis. So I'm in my home directory, which has these folders that are listed here. Your home directory will be different. You will see a different content, okay? Normally, the home directory is what we see when we open the tab files, okay? If you compare the two, it's just a list of the content of the directory I see here. Sometimes these are not in sync, but it should be something like that. Okay? Now we want to browse towards the folder where you have the data, which we can accomplish in two ways. Each of these folders, it's a hyperlink, you see? So I remember that I have my data under desktop, then water resources and hydropower, then practical activity. Here are the data. The Excel file is still open, so there's this temporary file. Let me close the file. It's not good to work. In case this window pops up,
No.
don't save. Okay. Were you able to navigate where you store the file, where you located the file, or in your system is different? Okay. Alternatively, you can press these three dots. Do you see these three dots here? If you cannot navigate where you store the files, some systems it might happen. Windows desktop is hidden sometimes. So if you press those three dots, a dialog windows pops up. Then you go where you want to be. In my case, I want to be here. And I press open. Okay? Perfect. Now, since the script is set in this way, it doesn't report the path. It needs to be working on this set as the working directory. We will set this folder as the working directory. How do we do? There's a gear here. We press the gear. Set as working directory. You click. This is RStudio, it's the interface. As soon as you click, you see the R command equivalent. Set was working directory and a path. The path, of course, will be different from me. Your path will be the path on your system. If we want to double check if we are actually there now as working directory, I can go up, find the previous command, and check if the content is what I expect it to be. If it's like that, we're ready to go. I see a working group here working, so are you all good or you have issues? More or less. No, more or less cannot exist at this stage because we still have to start. So
It's not exactly the same, but
just the Excel file?
no.
Mine is the
The
same.
PDF, the PDF is missing here, but I don't know why.
you don't have the
I
PDF?
don't have. Yeah, I have the PDF inside of my folder here, but I don't have here.
No, it's simply the line was not broken in the same point.
And then you should, okay.
You remember how a vector is listed? Or it's listed in a row until it hits the end of the line and then it goes below. Because that's a vector to him. It's a vector of character strings. To him, I don't know, to her, to it.
Now you should point everything that you store
these files as you're working on it. So there are three here.
You're all set instead?
Yeah.
I have to wait until everyone is with me. Che succede, Alan? What's going on here?
No rischio di interrumpere.
Well, this is, you already start with a high handicap, like you're a golf master, and you're working without some keys. It's difficulty level in a scale of 10 goes already up to 8 or 9.
These three are here. No, yeah. No. Proprio strano. Non ci sono I tre.
I get it.
Ah, okay.
We have it.
I didn't see the three dots, but okay. Yeah, I think it managed.
Here is my base.
Yeah.
Mhm.
Okay.
But I can't see.
Open. Open. Now you see the content. Now do you see the gear? Here, more. Press down. Okay. Do you read, because your font are too small, do you read set as working directory?
Okay. So that's
Set as working directory.
yes. I'll go it.
Good. Good. So, next thing I'm going to do is to open the script. Okay? So, I open up the script. This takes the upper panel here. Here you have an indication of the row line. Everything is green here because everything is commented. As I was saying, this script is heavily commented. So step by step, you have all the description of the computation performed. It's divided in points that are basically the tasks you have in your assignment. So point 1 meaning we are addressing task 1. Good enough? Good. So, library open Excel. This uploads the package. We need the package to read the Excel file. If I launch this command, it's exactly the same thing as going under tab packages, scrolling down, they are in alphabetical order. So this, I cannot resize columns, maybe not. Open Excel is here. If I click and put a tick mark here, you see library open Excel file. So this command is just to upload a package. Now all the functions in the package are part of your R system. You see this is an hyperlink that takes you directly to the help page of this package. We will use a few functions, but as you can see there are many functions available even for dealing with a worksheet with freeze pane, freezing them or not. So now we have the package uploaded, we can start. So I will comment quickly the lines as we go. If you see things that you don't understand or you don't follow me, please stop me and ask questions, as always. Line 14 is not a big deal. We save in memory 365. So I'm just storing 365 to have a more general coding, let's say, in an object called n. Here you have descriptions of the data set you'll be working on. We saw this already. Here, line 17, we set the target code. So target code is an object. Don't look at the dot. It's just another character. Okay, so target dot code means the code of the target site, and dot is just another character. And as I was saying, we will be focusing on Savio at San Carlo, number 5. If you put 10 there, you will be working on Borello at Borello, another catchment in our data set. Line 19, it's only to show you that, for example, with this package, you can get from the Excel files the sheet that are there. Daily_Q and descriptors. If you go back to the Excel file, I will close it right away. Those are exactly the names of the sheets, okay? Now, this is instead important. M, read Excel. This is a function to read a whole sheet, okay? So I'm simply telling the name of the file and the name of the sheet, which I just got here, if I want to make sure it has to be written exactly the same. Okay? If I send this line to the console, you remember how I didn't recall it today. Control and enter sends the line. I have my cursor there blinking, control and enter. In the global environment, under the section data, now there's M. What is M? Nothing else that the sheet read from the Excel file. We can read from an Excel file and we can also write as output, our output, we will see that on an Excel file. So this is the entire data set, okay? I have a preview of the first 50 columns, but of course, then I can go and check all of them. Okay, go back to the beginning of the file. M.target, again, it's my way of naming objects for the global environment. This is the portion associated with our target file of the whole matrix M. What am I doing here? M, open square parentheses, which. I don't think we ever, did we see this function? Which is a function that identify elements in object that comply some logical conditions, okay? So, if you recall, let me open up another script here where I note down things without, let's say, corrupting our general script. Let me save this as March 2nd notes. I will upload this file to the shared drive in our folder, okay? So, if you recall from the introduction to R, if I'm writing M parenthesis, square parenthesis, for example, 2, and then nothing, this is the second row in the matrix, okay? Since our matrix has named column, you see from the console that it's returning the value, but also the name of the column, okay? Here, what am I doing? Which elements of the first column of M are equal to target code. If I copy this function there, which elements of the first column of M are equal to target code, I get 22, 21, 22, 23, 24, okay? These are basically the rows which store data for Savio at San Carlo, 22, all the way down to 35. Sufficiently clear? This inside is a logical condition, right? I can launch only this part. It's a logical condition. False, 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 then true, 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 true. And the function which picks all the elements that are true in that vector. Okay? So if I go back here, now I'm selecting a sub portion of M, and in particular only those lines for which code is equal to 5. Then for these lines, get all the columns. If I run this command, the matrix I obtain is basically a sub-portion of the original data set that stores only the data for Savio at San Carlo. Sufficiently clear? Okay. Now, I get from column number 3 the observation years. Unique is a function that picks only unique values. In this case, it's not even important because every value here appears only once. But in case there was 2002 and then again 2002, it would have written just once 2002. It's redundant here. It's part of a previous script. I store in years the years of observation. So I can see now that Savio at San Carlo has 15 years of observation, and these are the years. Then I store, because I will be using it later on, the overall number of years in a new variable. So number of years is 15. And then finally, I create a matrix where I will be storing only the discharge values, because these are the ones I'll be working on if I have to build the flow duration curves. Okay? So matrix QDM, I am creating, opening a new data set to store only the discharge value. Matrix, we used the command matrix during our introduction, you remember? So data equal to NA means the data is not available, the matrix will be empty, with the number of row equal to 15 and the number of column equal to 365, because I have to store in there only the stream flow values. If I launch this line, I see in the data section of the environment an empty matrix. Okay? 15 rows and 365 columns. Clear enough? Good. Now I fill this empty matrix with the observed data using a control structure 4. We've never seen control structures before. 4, it's basically a control structure that performs a loop and repeats the same instruction until the end of the number of times we set. Okay? If I go on the nodes and I write, for example, 4, then the syntax for 4 is to input between round parentheses the name of the counter. I, to me, is the name of the counter in 1 to 10. So repeat 4 10 times, repeat for I value equal to 1, 2, 3, 4, 5, all the way to 10, a certain operation. For example, print I, if it works. I hope it works. If I launch this, command, you see on screen I printed 10 times, and it's the current value of the counter I. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? If the command can fit on one line, as it is in this case, okay, if it fits in one line, this is the syntax. This is how you use a control structure. Sometimes there are more commands that you want to repeat a certain number of times. In order to group lines, you use curvy brackets. Okay? So, curvy brackets are like this. In Windows system, Alt group, then Shift, then square parentheses. This is a curvy bracket. Print I and print I square. Close the curvy bracket. Okay? This is a control structure that performs all the lines between curvy brackets from counter I, index I, going from 1 to 10. Of course, this instruction sits on several lines, so if I want to send it to the console, I have to select them all and send them. And this is the output. 1, 1, 2, 4, 3, 9. Okay? Sufficiently clear? Yes, I'm coming. I saw the hand for control structure.
It's just how do you do the curve bracket?
Okay. Alt group. You see Alt group, Alt GR on your keyboard. Normally it's on the right side, lower portion of your keyboard. Maybe French keyboard is different. No. I don't think so.
It should be the same.
It's a Mac?
Yeah, it should be the same.
Windows biased. Option. Option key on the right.
Oh, okay, perfect.
Option, then Shift, and then...
It's option without shift.
And it comes out curvy?
Yeah.
That's weird. Are you sure? Let me see. Option without shift. No, it comes out square.
Oh, for me, option shifts is square, and option without.
You French people, I don't know. I'm just kidding. The important thing is that we found a way, okay? Good, good. Very good, so I'm going back to the original script. Look, for loop, index I in 1 to 15, right? Then space, QDM, square parenthesis I, so get the I row in that matrix, and what are we going to put in the row number I? Sort. What do you think sort does? It sorts values, either in ascending or descending order, depending on the optional argument you see here. So decreasing equal to T. You know what T stands for? It's an abbreviation of true. Decreasing equal to true. So using this function this way will sort the values in a vector in decreasing order. Okay, so not only we pick 1 year of observation and we store the discharge value in QDM, before doing so, we also sort the values in descending order. Okay? So, if we send this comma to the console, this will fill up completely this matrix. Let's see what happens. Tell me if I'm not clear, okay? So I'm sending line 32 and then going back to check the matrix.
If we don't write the decreasing equals to true, so it would be default and be ascending.
I don't remember what the default is, so when in doubt, help. When in doubt, we can go here and we notice that the default value is false, which you can abbreviate with F. So capital, uppercase F in R is false, uppercase T in R is true. Okay? If I omit that argument, then it will sort in increasing order. Okay? Couple of things I want to show you. Now, each and every row in our matrix stores the observation, the daily stream flows for Soviet San Carlo for a given year, and the first value here is the maximum. Okay? So for this year, which was the first year, I don't remember, I think 2002, the maximum is more than 305 cubic meters per second. Then, of course, if you scroll your matrix and you go at the very end, last line, 300 vector 365, this will be the minimum. The minimum is not even 2 cubic meters per second. So this is the range of variability of stream flows for the same river, same cross-section in 1 year, more than 2 orders of magnitude, what I was pointing out before. This is why flow duration curves we plot on a semi-log vertical axis, okay, because there's a huge variability. Sufficiently clear? I see many wrinkles here. So it means that there's something unclear.
No.
When I see wrinkles here, it means that something is unclear.
Clear.
Clear? Okay. So keep your eyebrows relaxed. Good. Otherwise, the professor gets concerned. Good. So if you think this matrix here contains already annual flow duration curves, right? If we plot these values according to their duration, what we get is a flow duration curve for a given year. Okay? Good. So let's keep this on hold for a moment and let's extract the percentile flow duration curves from this data set. For example, median annual flow duration curves, it means that duration-wise, and duration-wise means column by column, because each column is associated with a given duration, right? And which we will see how to compute. But in order to extract from here the percentile annual flow duration curves, I go on each and every column, for example, median annual flow duration curve, and I extract the median from here. Okay? Then I want to store this in a new object. This new object has 365 columns, and then many rows as many percentile annual flow duration curves I'm going to save, I'm going to construct. In our exercise, we are referring to median, non-exceedance probability equal to 0.5, and then in order to characterize wet and dry years, 10 percentile and the other way around actually, respectively, wet years 0.9 percentile, dry year 0.1 percentile, so 3 in total. We will store this information in a matrix with 365 columns and 3 rows. This is why on line 38, I'm storing in memory the 3 non-exceedance probability value of interest. I'm storing them in a vector p-values. P-values is a vector with 3 elements with the 3 non-exceedance probability we are interested. 0.5 typical year, 0.1 abnormally dry year, 0.9 1 in 10 wet year. Okay, I'm repeating things as we go. Also, in order to have a flexible coding, I'm saving the value of non-exceedance probabilities, 3, in this variable here. And then, as I was saying before, I'm initializing a new object. The new object is called Q, that stands for stream flow, PRC, that stands for percentile. Okay? Q percentile is a matrix that initially is empty, like before. It has 3 rows and it has 365 columns. Okay? If I launch this line, here it is. At the moment is a logical matrix because it's empty. It doesn't know if it's number, strings, it became logical. Don't worry about this. If we look at it, a matrix with 3 rows and 365 columns. Then, for the sake of clarity, I'm assigning names to rows in order for this matrix to be more clear. And I'm using as row names for this object p-values interpreted as characters. Okay? P-values are numbers. But if I use the command as character, it will convert these numbers into text strings. And so I can use them as labels. If I launch row number 42, this is the result. 0.1, 0.5, 0.9. Okay? So I remember that the second line is where I store the stream flow values for a typical year. Whereas the first row is where I'm going to store the stream flow value for a dry year. Okay? Very good. Very good. Now there's a for loop with another function. We haven't seen this function yet, so let's have a look at it in our notes. Question for you. Where in our general matrix with all the stream flow value, which is the column associated with the lowest duration? Low duration curves that look something like this. Duration, 0, 1. Stream flow in log scale. They look something like this. Where in our QDM object, the one that contains the sorted value row-wise, where is located the value with the lowest duration possible?
The highest.
The
highest.
The highest. So where's the highest? Which column number? The first one, right? In the first one, I see the highest value, so it will be the value associated with the smallest duration, close to 0, not 0 for the reasoning we mentioned last week, right? Okay, so if I want to characterize the high flow value stream flow value with the lowest duration from the data set. For a typical year, I have to compute the median, right? This is what I would do. So if I want to compute the median, I can use the function median. It's already there in R. I can use it. QDM, open square parenthesis, look at all the rows, so comma, and the first column. Okay? This is the median value, right? So if I open this matrix here and I look at the first column where I stored for each and every year the largest value, the median is around 114 cubic meters per second. Whereas the minimum value am I unclear? I hear, everything is clear? Whereas on the very same column, the minimum value is equal to 21. So the largest stream flow in a year of our observed data set can go as low as 20 cubic meters per second. And the maximum one, what is the maximum one? The maximum one is 387, almost 400 cubic meters per second. And we're looking at a very well characterized variables. We're looking at the maximum, the largest daily stream flow in a given year. In our sample, it varies from 20 cubic meters per second all the way up to almost 400 cubic meters per second for the same river and the same cross section. Okay? In the script I gave you, we use the function quantile. Quantile is just the same as percentile. A quantile or a percentile are synonyms in statistics. So quantile extracts from a given data set the quantile associated with a given probability value. How do we use this function? So median, min, max, and quantiles. How do we use this function? I have to provide this function with the data set, for example, the largest values, the maximum annual values, and then the probability. The second thing I have to assign is the probability. Probs. See? Probs, argument probs is the probability value. Probs 0.5. If the probability value is 0.5, what is the quantile I'm extracting from the data? 50%. So what is the name for it? And in fact, here it is, same value. Okay, so the median is the quantile associated with a non-exceedance probability of 0.5 or an exceedance probability of 0.5. Okay, but I can also provide the function quantile with more than one value of probability. So if I write something like this, quantile, instead of 0.5, I write C, open parenthesis. You remember function C, lowercase c? Combine. It combines elements in objects in a larger object. So C 0.1, comma 0.5, comma 0.9. Okay? If I send this line to the console, this is what I get. These are, for the annual maxima, the 10 percentile, the median, and the 90 percentile. So the annual maxima in a very wet year, a 1 in 10 year, the annual maximum in a very dry year, a 1 in 10 dry year, and what happens, 115 cubic meters per second, in a typical year from a climatic viewpoint. Okay, is this sufficiently clear? Now the for loop will perform this operation for each and every duration. It means for each and every column in your data set. It will start with column number 1, 2, 3, 4, all the way to 365, and store this output into the matrix we just created. Tell me if I'm not clear enough. I'm saving this, and I'm going back to the practical activity. See? Look, this time I call the counter ID in order to remember that it's associated with the duration. So for ID that goes from 1 to 365, what am I going to do? I'm getting column ID of QPRC, all the rows, and I'm storing in these 3 rows the quantiles associated with the p-value. Okay? Quantiles extracted from the observed data. So, column-wise, all the data I have in my large QDM dataset. If I perform this operation, the object here that I call Q percentile fills up with values. Okay? So this is the annual maximum daily stream flow, the median value, the 10th percentile, and the 90th percentile, and then so on and so forth for all the duration values. We now have all the things we need to plot the annual flow duration curves. It's very easy to create a vector for plotting the period of record. We have to discuss a bit how to compute the duration, and then we will be able to plot these curves on diagrams. Before getting there, I want to show you something. Of course, first time we are working in R, I am trying to be very detailed, right, in my explanation. Still, something you may miss. Still, something I'm saying might not be clear enough. Nowadays, we have very powerful tools we can use when we are coding, when we are programming. I'm talking about large language models like ChatGPT, Gemini. Do you use these things in your? You can say I do. I'm using them. Yeah. I also work as an editor of for a scientific journal, and it changed my life. Now writing emails in perfect English became really a piece of cake. But they can do several things, included helping us to understand what a script is doing. For example, line 44. Professor told me what it does, but I have no clue. I don't remember. I don't want to go and check the recording in Virtuale. So instead, I'm opening up, if I can. Okay. I'm opening up ChatGPT. A version of ChatGPT, which is not the freeware one, it's not also the premium one, it's something in between, you have access to as students of Unibo, okay? If you go to Office 365 and you use the chat of Office 365 as Unibo student, so register with your Unibo credentials, okay? I'm registered as Attilio Castellarin using my Unibo account. You can do the same using your Studio Unibo account. And then it's better to interact in English with these things, which is good for us. And then you write, please, which is not really necessary. We are interacting with a machine, right? So, but why not? Please comment and explain step by step the meaning of this R command. And you can even write wrong English, it will understand. Of this R command. And then column, and I'm pasting here the line. Step-by-step explanation. This starts a for loop that iterates over integer values, id 1, 2, 3 up to n. So the loop is repeated n times. So you get a detailed step-by-step explanation of any part of the script I provided you with. These are very important tools. Another thing, it's not very important nowadays to master several programming languages. Why? Because these tools can do the job for you. If you want to have the same command in Python, you can ask the large language model to generate the Python equivalent. Okay, here it is. Python is a very similar language. These are all Unix language-based object programming languages, but I think these tools are enormously helpful, because a colleague of yours might be more skilled in Python. He or she will pass you codes in Python, and instead you know R for your university studies. You can easily have the script or the snippet or the command converted back to R. Okay, I wanted to show you this. Good, good, good. So, line 47, going back to the script. Do you remember how the duration is estimated? Because we're almost there. We have data for plotting annual flow duration curves or percentile, but we need the durations to create this plot. We need to associate to each and every value a duration value. So if we go back to the relevant slide, I provided you during theoretical classes with an estimator of the duration. I used the Weibull plotting position to compute the non-exceedance probability. Non-exceedance, but look, this applies when you order your values in ascending order. Here, instead, we used a different sorting criterion. We sorted them in descending order. Okay? Is this a big deal? No, it works the same. We have to be careful and look what sorting criterion we apply, right? So if we sort in descending order, so we sort the discharge value like this, Q1 is larger or equal than Q2, which is larger or equal than QI, larger or equal QN. I'm putting the rank within parentheses to stress that this is a sorted sample, not a sample in chronological order. That's a notation that it's very common. Where I is the rank, in our case, rank equal to 1 means maximum, while rank equal to n means minimum. I didn't stop. I am planning to stop the class before the time. I skipped the pause. I was about to ask, is that okay with you? But since we skipped the pause already, there's no point in asking. So, this will be the value associated with the lowest duration, right? What is the meaning of the duration? The meaning is the exceedance probability. The exceedance probability. So we were sorting in ascending order, and the exceedance probability was 1 minus the rank divided by n plus 1. If we sort the other way around, so in descending order, the exceedance probability will be just this part. That's it. So we compute the duration. D will be equal to 1 over n plus 1, and in general, I over n plus 1 if we sort in descending order. So just be careful, okay? And, well, if we are working with annual flow duration curve, n is equal to 365, right? Whereas if we're working with period of record flow duration curve, n is equal to what? Question to you. Equal to what?
Would you repeat again?
I'll repeat the question. When we apply this estimator of the duration of the ordered flows, n is equal to 365 if we work with annual flow duration curve interpretation, because we have 365 possibilities. If we work with the other interpretation, period of record, meaning all the data you have in a single sample, n will be equal to what?
366?
No.
Just, okay.
You remember the definition of the period of record flow duration curve? You take all the observations you have in a given, at a given stream gauge, and you put them in a single sample.
The summation of the total numbers.
Exactly. The overall sample length.
Yeah.
You have 15 years, it will be 15 times 365. Sample length. Okay, and this is what the script performs. This is what the script performs here. So this object will contain the durations for the annual interpretation. from 1 to 365 divided by n plus 1. Keep in mind that mathematical operators in R have a hierarchy, okay? So if I write something like this, there's a column, a ratio, and a plus. First thing will be performed is the column. So first thing will be performed is the generation of a vector of integers from 1 to 365. Then the ratio and the computation of the denominator only afterwards. So if I launch this, it will store in memory a vector with 365 values. If I want to see this value, I can do. The first one will be the duration estimated for the maximum. So very small duration, almost zero, not zero, because next year I could observe a discharge, a daily stream flow for that catchment that is even higher, okay? Not zero, but almost zero. It's 0.003, more or less. And then, of course, the duration linearly goes up, and the duration associated with the minimum value, is almost 1, 0.997. Not 1, but almost 1. Okay? Then, we're almost there. I'm creating a vector with all the observation because I want to plot the period of record flow duration curve. And this is easily done by destroying the structure of QDM. If I write lowercase c and use QDM as the argument, QDM is a matrix. But if I use C combined, the matrix will be destroyed and it will become a vector. And then sorting this vector in decreasing order. If I launch this line, see, these are the observations for plotting the period of record flow duration curve. And it's a very long vector. It has 5,000 and almost 500 observations. Why? Because we have 15 times 365. It's sorted in descending order. So this is the highest value in the sample. This is the second highest value in the sample, and so on and so forth. Can we use this duration vector to plot this curve? No, because we have a different number of elements. This is why I'm storing the sample length in n_POR. Why? Because this code is flexible, so it has to work for any of the catchment there. They have different years of observation. So in this way, without changing anything but the line where we assign the target code, everything will work smoothly. So I'm storing the total number of observation in this integer, and I'm computing the vector of duration for the period of record flow duration curve using exactly the same definition, from 1 to 5,500 divided by 5,500 plus 1. Same definition. Okay? And of course, in this case, the duration associated with the maximum will become much, much more smaller, closer to 0. Okay. Do you have questions on this part? Then I'm looking at the script. From line 57 down, there are commands for plotting a flow duration curve, okay? With a lot of customization. We didn't see how to open a plot in R. It's very, very simple. Look. I am stretching a bit this panel here because the plot will end up here. So, for example, let's just to show you how it works. If okay, sometimes it stops working. If I want to plot the POR, so the period of record flow duration curve, I simply open up a new plot, and then the minimum amount of arguments I have to give are the X values and the Y values of the series, okay? As easy as that. So the X values, if I want to plot the period of record flow duration curve, are this. So I simply have to start writing D underscore, and then I press tab, the key tab. If I do, I see everything that starts in this way, which is in memory. I told you this already? Okay, so I select this, comma. These are the X values. Now the Y values. The Y values is this huge vector I have here. FDC observation. So I start typing FD and then I press tab, FDC observation. And this is your flow duration curve. Okay? It used markers because I didn't tell you R anything. If I want a line, I can change it into a line. It used as labels for the axis the variable I use because I didn't tell it anything. And above all, it used a natural scale. So you can see what I was mentioning before. If you use a natural scale, high flow are so larger than low flows that all this part is squeezed, and I cannot even tell if these are zeros or some values. So if I want, for example, to use, from here it will work for sure. If I want, for example, to use a line instead of markers, I simply write type and then L between quotation marks. This will turn the markers into a line, okay? Of course, you can browse previous plots. They all stay in memory as well, you see? If I want to plot the flow duration curve on a semi-log plot, I can do that as well. I seem to recall that the argument is log here. And if I want only the vertical axis as a log scale, I simply write quotation mark Y. And this will change the representation into a semi-log. Of course, there are some zeros in the series. I didn't point this out, but if you look at the data and you go where the minima are, so let's say here, you see that for some years there are some zeros. So I have asked R to plot zeros on log scale, and of course I get a warning. But it's a warning, the plot is there. Okay? Very good. Do you have questions on the things we've seen? Okay. The rest of the script, if you want to have an explanation on the meaning, you can use, for example, ChatGPT, simply plots the data. So figure 1 will be the empirical period of record flow duration curve. I am stretching the plot panel so that it works fine, because with this resolution it would place the legend in the wrong spot. Plot, axis, manipulate the axis. Grid adds a grid, and legend adds a legend. If I launch all these lines, I get nothing. Because I didn't launch lines from 59 to 61, which are for customization of the diagram. So first thing, I launch this. And then I do exactly as I was saying before. And this is a representation of the period of record flow duration curve. Okay, now I change a bit also the labels. Now it reads discharge in cubic meters per second. Here it says duration. Here you can see that on the long term, in these 15 years, there are some intermittent period for that catchment. So these are the zeros. You see the curve goes down, it has dropped. And the duration 1 is here. It means that there are some zeros there, as we saw. And this is a representation of the curve. I would like to stop here. On Wednesday, well, we could finish this, but Alan, I think we will just see the 3 other plots, wrap up a bit, and go back to theory. So for a 10-minute time, I think there's no need for you to join us. So on Wednesday, please bring your laptop. Sorry about that. We will finish these plots, see a couple of words, and then go back to the theory. Okay? Ciao.